In this slide, what I would like to do is talk about the importance of a hidden layer. Say we have the problem of finding X and Y. So if you remember talking about logic gates, what AND does is it throws out a positive signal only when both of the inputs are positive. So if my first input X is negative and my second input Y is also negative, the output becomes negative, 0, right? If my first input is positive, second is also positive, then the output becomes positive. In all other cases, the output all becomes negative. So this is the standard AND function. Now, AND function can be very easily represented by just using a single neuron. Say we have one neuron that looks like this. It receives input from your X and your Y, and let's say we have a constant bias, and say these are the weights. Now, the output, let's say, of this function is simply X times this weight 20 plus Y times this weight 20 plus this constant 1 times minus 30. So this is the output that we have, output in this case. Now when X is 0 and Y is 0, clearly the sum of 0 times 20 plus 0 times 20 becomes 0, plus this is minus 30. So the output becomes minus 30, which is less than 0. So if we have the weights like this, our neuron can successfully produce a value less than 0 if X and Y are both 0. If one of them is 1, let's say if X is 1, then the output becomes 1 times 20 is 20, plus 0 is still 20, and then minus 30 is minus 10. So this is minus 10, which is still less than 0. So the network still produces a 0 when either one of the X or Y are 0. Only when X and Y are both 1. So if this is 1 and if this is 1, then this becomes 20 plus 20, 40, and minus 30 becomes a positive 10, which is more than 0. So only when X and Y are both 1, then the network produces a positive value, right? So we can see that a single neuron can effectively act as an AND function if the weights are put appropriately. So if the weights are there in this way, then it represents the AND function. Now let's look at the other function OR. So if you remember once again, OR is a function that leads to a positive output when either X is positive or Y is positive or both of them are positive. Now once again, we have a single neuron and we will see that even the single neuron also can represent the OR function. All we have to do is change this minus 30 to minus 10. Now, when X is 1 and Y is 0, this becomes 20 plus 0 minus 10 is a 10, which is more than 0. So when one of them is positive, this value becomes a positive value and it represents the case when the output is 1. If both of them are positive, so when X is 1 and Y is 1, then the sum of these two become 40 and minus 10 is 30. So 30 is still more than 0. So this also represents a 1 and it captures that, it captures the OR function. And both of them are 0, so X is 0 and Y is 0, the output will be, so the sum will be 0 times 20 plus 0 times 20 is 0 minus 10. So the output becomes minus 10, which is less than 0. So it represents the case of 0. So we see that even a single neuron can represent the OR function as well. Now, another interesting function in this binary calculations is the function that results to a 1 only when your X is 0 and Y is 0. So when for not X and not Y, you want a 1, but for all other cases, you want a 0. So even such a function can be represented using a single neuron with the weight set to, we set this to 10 and these to negative 20, and we can represent this not X and not Y function. Now let's see if we can represent this binary function XNOR using a single neuron. So XNOR can be broken down into A and B or not A and not B. Turns out XNOR cannot be solved using a single neuron. In other words, if we want our output to be 1 when x is same as y, so when x is same as y, then the output is 1, otherwise the output is 0, then to represent such a function, which is the XNOR relationship, right? XNOR relationship, a single neuron, one neuron cannot accomplish this. We need to have at least 3 neurons sitting like this. So the first neuron has to be the AND function that takes inputs from all three, computes the AND. So this is the output of AND. We need the second neuron that computes the not X and not Y. This is our second function there. And then we want the OR sitting at the end that serves as the ORing of and not A and not B. So A and B, this is represented by this neuron. Not A and not B is represented by this neuron. And this OR is represented by this neuron. So here what we also have is you can see that this is the hidden layer of the neuron, right? So this is your output layer, this is our input layer, and in between these two are the hidden layers. In other words, if our data has patterns like these, if the pattern is like this, then single layer neurons or methods like logistic regression or linear regression cannot solve if the data has patterns like these. So this is exactly an example that demonstrates the power of a hidden layer in a neural network.